talk is about trying to it's about my can you edit this? I thought I would try my hand at kernel hacking. So I went to the Junior Jobs webpage and picked out a suitable task. And that'd be this task here. I cannot believe this is 10.8. Let me see if I can get the...
You want to set it, open the system preferences?
It's on preferences. I'm... display... Okay, because I don't believe this is optimized for Creston, whatever the hell that's... 1080p. That's a lot better. Okay. Yeah, all right, fine. Okay, now bring the web page back up. Okay. So I figured I'd try this task because it looked simple enough to do. I can go and here we go. The only requirement is C programming skills, and while I have not done C programming in more decades than I would care to admit, having focused primarily in C++ in recent decades, I figure it's like riding a bike. You don't forget how to do that. So the task is really quite simple. There are situations where a file descriptor table can be shared by multiple processes, usually after a fork or something, or creating a new thread. And there are cases where, and because of this, when the file descriptor table has to be reallocated to be bigger because you open a lot of files, it can't free up the old space. It has to hang on to it. It's not a real memory leak because when all the processes die, then it can be reclaimed. But the problem is that in the name of performance, this table is accessed by lockless means, which basically means that you simply do not know if there is another process that's actively accessing that table, therefore you can't free it up. And if you force it to use a mutex, well, that slows things down a lot because this table is accessed very, very heavily. So what this points out is that there are several conditions in which we can know that you can free up the old table. Like if there's only one process, that hasn't been forked, and there's only one thread, in which case there can't be anyone else accessing it, therefore you can free it up immediately. I doubt this actually makes any difference. I mean, in the real world, obviously, it requires a very specific set of circumstances, and the amount of memory that's being tied up is not a whole lot, but it is what it is. So, okay. I decided to take that task, and of course the first thing you have to do if you want to do BSD kernel development is you have to check out the current head and build it and set it up to run it. Now, what I have at home is a machine which actually runs BSD. Of course, it runs the production version of BSD. This right here is essentially a clone of that machine running under VMware Fusion. I could, of course, technically run the FreeBSD head under Fusion as well, but there's a much better way of doing it, and that is to run it under BSD using Beehive. And so that's why I have this set up here. So in order to do that, first there's this one-time setup I have to do after each reboot. So first I have to load the VMM kernel. You want the font a little bigger. Let's see, this is I'm going to be opening up a lot of files. Now let me go change the effective resolution of the display and make it lower. So let's scale it to, let's try 720. That'll make everything bigger. So is that much better? Yeah. Okay. Oh no, these windows are too big to fit. Come on. Why won't you let me do that? Well, whatever. So the first thing, of course, you have to load the kernel driver for VMM, for Beehive. Then you have to create this network tap so that the Beehive machine can access the network. And then there's some other miscellaneous stuff here. I basically copy and pasted these from a Beehive setup instruction page I found. And the last thing is this line here. Guest.img is the file system for the Beehive virtual machine, and when the virtual machine is not running, I want to be able to mount the virtual disk directly in the host system. So this makes it a lot easier to do things like doing an install world, for example. So I only have to do that once per reboot, which doesn't happen all that often. And of course, I could go and start up Beehive. And so, well, first show that. So right now, the virtual machine is mounted under MNT. So this is the virtual disk. And then I go and start Beehive. So that's 12 current.
So Beehive doesn't exclusively lock the init file?
Yes, it does. Okay, should explain here. So basically, I modified the script, and maybe too hard to find it. Basically, I modified this standard script. I made a copy of it and modified it so that it unmounted. Is it too hard to find out where this is? Oh, there it is. Okay, so I modified a script to unmount MNT. So yes, it does require exclusive access to it. And then when the virtual machine ends, I remount it. So the script takes care of that automatically. So right now, MNT is empty. And so Beehive is running there. So start with the changes I actually made. So that, of course, is under the source tree. Those are all the files I modified and added. So source, kern. Oh. Boy, why can't I resize this? That works better. Oh, that's why. So this is the kernel code that grows the FD table when you open one too many files. And so it does which is pretty straightforward. So allocate a new map only if the old is not big enough, and then if it's and then right here is the code that I added, which would probably be easier if I did a diff actually, but anyway. So the bulk of the code I added is right here. So first we checked the thread count. And so if the thread count, so if there's only one process that's referring to this, this file descriptor table, And this primarily happens when you do an R fork, is when you create a process that shares the file descriptor table with its sibling, or the number of threads is equal to 1. Well, then we come down here and we can free the table immediately. Otherwise, we basically have to chain the tables together so that when the ref count goes to 0, we just delete the entire chain. Now, one of the interesting problems here is, and I'm going to spend most of my time on this, but this is basically the bulk of the code right here for this. But the question is, how do you know it's working? And this is a common problem with kernel changes. Sure, I can write a bunch of programs which do R forks and thread creates and create a bunch of files and close them and what have you. But how do you know it's actually working? That is, this is accessing the table without locks, which means it's susceptible to non-deterministic behavior, and you can cause a crash. So how do you prove that that's not possible? And unfortunately, unless you basically run the test a million times, you might not be able to show that. So what I figured is, well, you need a testing framework which will help answer the question, are you releasing the old tables when you're supposed to be releasing them and not sooner? And I looked in the kernel and I could find no suitable framework. And I looked to see what kind of regression tests and unit tests existed for the kernel. And to my surprise, there really aren't all that many, actually. So I figured this is an opportunity to provide a solution. Now, right here is what I came up with. This is a logging macro. If you do a release build, this macro is defined as nothing. It just disappears. But in a debug build, like what this is, this will format and put this message someplace where a userland process can retrieve it. And this userland process, after creating a bunch of files, will then see if the expected messages have been logged for it to pick up. So for an example, for the test program, where did I call it? Right. Okay, so that's this right here. So first it has a little helper function that just basically creates a whole bunch of files until the file descriptor table is reallocated. And how does it know that? Well, actually, I guess I should move further on down here. And it knows it from this. I added a new special device, character device file called devk-testlog, and that's where that message shows up from that macro. So the test program opens it up. It then does something that theoretically produces a message, and it reads from that special device, and until it actually sees something, it knows that the table has not been regrown, reallocated, and therefore it just goes ahead and does a pipe call to create 2 new file descriptors. And once that causes the table to be doubled in size, a message is logged, it sees it, and then it goes ahead and echoes it to standard output. So I have a whole bunch of scenarios. So test 1 simply does this in a single process with a single thread, which means it is expected that the table should be freed immediately, and in fact it looks for that right here, in which it goes ahead and looks for that message, and if it didn't see it, you have an error. The second one is single process, multiple threads, in which case the old file descriptor table should not be released, at least until the process completes. And then for the third case, you have a multiple process context where it's using rfork. And if I run it, we basically get this. Whoops. And so these are all the messages that are logged by this ktestlog macro. And so in the first test case, they're freed immediately because it's impossible for the old memory to be used by a different process or thread. But for the other cases, it's not freed immediately, and they just basically accumulate until the process dies, and then they're finally freed all at once. And again, same thing for the rfork case. So this test proves that the old tables are freed when they're supposed to be freed and not sooner, thereby giving you a high level of confidence that I did not introduce a race condition. And even if I did, you know, the odds are very low that this one program will crash. So it's very important to actually be able to prove, some definition of proof, that things are behaving the way you want them to behave. Because just simply, you know, running a bunch of random stuff, you know, seeing if you get a kernel panic or not is really not a way in order to verify that your code is correct. So you can then look at the implementation, and that's what all these added files are for. I mean, syscomp files have to add an entry for each file I add so that the build system knows about it and actually builds it. So we have sysdev is where, so this implements the character device driver. And, oops. So that's sysdev, ktestlog, ktestlog. Let's see. Okay. So this is the device driver. And again, I just found something like the dev null device driver and adapted it. You know, it's always easy to start with an existing driver that kind of sort of does what you want and figure out how to extend it. So you know, you have to define all the various entry points that you want to implement. And of course, you have to handle the open logic. So what this does, how it works, I mean, obviously, you would like to be able to, you would like to run multiple unit tests simultaneously, which means that the log messages that are produced for each unit test need to be separated from each other. You don't want to get intermixed. So what this does is that it builds a data structure, right here, ktestlog create queue, and this is associated with the thread that opens the device. So each open in its own thread will produce its own data structure, and it's associated with that thread. And in fact, that's what this call here does, devfs set cdev private. It basically takes this data structure and associates it with this file descriptor, this open file descriptor, which can then be retrieved later on. And then for close, don't need to do anything. For poll, which I haven't implemented yet. For read, it's pretty simple. You go fetch that data structure and then try to read and retrieve a message if there's any that has been queued. The I/O control, I haven't implemented that either. It might be nice to implement KQ as well, which I have not done either. Or select for that matter too. And then you have, and then this is a callback that gets called in various events. So you get called when you get loaded, because this is loaded when the device is open for the first time, and then when it's unloaded, and that's pretty much all I have to worry about. So the character device driver is pretty simple. It doesn't have to do much. And the bulk of the work is done in maintaining that data structure. So let's see, so that, start with a header file first, so that's in whoops. Okay. So this defines the global data structure. I use the if-def invariance. Invariance is defined only for a debug build, basically. In the production release build, this would not be defined, and all this code basically disappears. It's possible that maybe you should use something other than invariance, but basically it's just simply hitchhiking on what was already there. So we define the k-test log macro. So you pass it the thread descriptor block, the level of the message, and then a format string, and then arguments to be passed to the format string. And of course, it's declared to be printf-like, which it is. Then you have the close queue, and then this is used only internally by the driver itself. So this is used by the macro. This is used internally by the driver in order to create a queue, destroy the queue, and read the queue. And if this is a production build, then the macro simply defines to nothing, and all that very expensive logging code just disappears. And theoretically, if this macro was put everywhere, because this was used to implement hundreds or thousands of unit tests, and so you would have to put these macros all over the place, I can imagine that it will significantly slow down the debug build. Of course, a debug build is already pretty slow compared to a release build, but that's the price of being able to do proper testing. And then this closed KQ, it just simply turns into an inline empty function, which of course also effectively makes it magically disappear. So the other file I modified was kern thread. And this is where all the threading code is kept. So basically, when a thread exits, it basically calls close queue, because that's when the thread is gone, if there are any messages that have been logged for, then no one has read them yet. Well, the queue is not actually eliminated until the thread it belongs to exits and all open file descriptors referring to it are gone. So only when both things happen is the queue is actually deleted. And that's the only change here. And so the other last big file is this kern. And this implements the queue. Again, only built if it's a debug build. And I had to do a lot of digging around to figure out how to do this stuff here. I have a hash table that's basically a global variable. And basically this, and it has a mutex on it. So this call right here goes, and during system boot, this will basically cause this global lock to be initialized. And so this macro magically causes it to all happen when the system is booting. Then I have a queue and an entry for the queue. And again, this STL queue head, this is again a standard data macro or data structure macro that's defined in the kernel. And then you have to provide a hashing function, and this is how you define a hashing function for that hash table. It reminds me why C++ is not a bad language to use now and then. But unfortunately you can't use an STL unordered map when working on kernel code. Then you have, again, this is another macro that causes stuff to magically happen during the boot process. And that causes this function to be executed, which allocates and initializes the hash table. and then implement the functions to log a message. So the first thing it does, of course, is grabs a spin lock, finds the queue for the thread. If it didn't find it, or because the device driver, the ktestlog device, was never opened for this thread, this will return null. That means that means that there's no one will ever read this message, so we just go and throw it away. And also, if the level is too high, that is, it's not important enough to pass on to the test program, we'll go ahead and drop it as well. So we just then release the spin lock and return, just drop it. Otherwise, we increase the ref count and then drop the spin lock, because you're not supposed to hold a spin lock for very long. But this ref count will stop the data structure from being deleted should the thread exit and any file descriptor referring to it gets closed. So this is the third thing that will keep it alive. And now that the spin lock has been dropped, we'll do the potentially expensive operation of an sprintf, which also will allocate memory. And in fact, it is illegal to call this while holding a spin lock. Actually, you'll get a kernel panic if you do hold a lock while calling this, because this allocates memory, and a memory allocation can block. It may cause the thread to block, even though it's a kernel thread, and you cannot block a kernel thread while it's holding a spin lock. Which is why in fact, I found this out the hard way. I got a kernel panic. And now that's allocated, they'll go and allocate memory for an entry in the hash table. Go ahead and stick all the pointers in there, and then I re-grab the spin lock, and then I go and insert this into the hash table. I can then decrement the ref count, release the spin lock, and then the ref count's now 0. Well, it turns out that the thread has exited. All the file descriptors have been closed, so destroy the queue. It has outlived its use, even though we just added a message. And then for closed queue, so this gets executed when the file descriptor is closed. Again, pretty obvious. Grab the spin lock, tag it closed, release the spin lock, and then we remove it from the we remove the hash table from the global structure, although we don't delete it quite yet. And then the create queue. So again, we allocate memory. And don't be fooled by this malloc here. This is not the C runtime library malloc. The kernel does not use the C runtime library. It has its own runtime library, which implements many of the functions that are in the runtime library, but they are specific to the kernel. So there's a malloc here, but it's doing memory allocation inside the kernel itself. So allocate the top level data structure for the hash table, and go ahead and initialize everything. And then we can grab the spin lock. And we look to see if there's already is one for this thread. Well, if that's true, then well, we can't have more than one for a thread. We will reuse the one that already exists. And we can't check beforehand, because unless we hold a spin lock, obviously we can have no way of knowing or prevent another thread from creating this hash table. So basically we have to create it assuming that no other thread is doing it right that second, and then once we get the spin lock, we can see whether there's a collision, and if so, the first one to have grabbed the lock wins. But that's okay. So we then go ahead and free it, and then make it official. Actually, right, that's actually not quite true. What happens in that case is the open fails. So you can only have one file descriptor on that special device file per thread. So the second attempt to open that up will fail. That's actually what happens. You'll get an error code back from open. And then for destroy, again, we basically just simply do the ref count and the close flags, and basically we're seeing whether anybody actually, whether it's still truly live or not. And if it is live, well, we have to defer it. But if it's no longer live, then we can go ahead and actually free up the memory right away for read. This is perhaps the most complicated routine of all. And that's because read gives us a rather complicated data structure, since all forms of read come through here, and that includes the read v as well. In fact, we can't really tell whether it's a read or read v, because a read basically creates a one element array and then does a read v internally anyway. So, first we check to see how many bytes we're being asked to read, and if it's 0, well, do nothing. In other words, we grab the lock, we do a kernel assert. The ref count had better be greater than 0. Otherwise, we are trying to read a queue that has already been deleted for this thread. That should be impossible because there's an open file handle for it. And kassert is a kernel macro, and which will cause a kernel panic if the condition is false. And if it turns out that the if there is no queue, then it basically goes and returns immediately, and either with a right. I wrote this code a long time ago, and so it's being a little fuzzy here. If the queue is empty, obviously there's nothing to read. And so if the queue has been closed, then we return 0, end of file. Otherwise, we return E again, basically say try again later. There's no message currently in the queue, so try again later. So it's like reading a pipe, but within non-blocking mode. And if I ever implemented the the syscontrol, or it will you can put it out of blocking mode if that suits your purposes better. And so now that we've done that, we want to do as little work as possible while holding the mutex. So the first thing we do is we go ahead and swap the list of entries with an empty list, and then drop the mutex. So we are now free to do as much work as is called for to copy the data back into the user process, which could potentially be very expensive depending upon how many messages have been logged and how big of a buffer has been provided. So you don't want to do that while holding the mutex, a spin mutex. So just simply replace it with an empty list, and now we have sole ownership of of the list that was in there. And I have a bug here that I point out that I need to fix someday. And so basically, you just go into a loop, and you see how many bytes are left to read. And then you move data from the queue into the user process, and that's what this function does, UIO move. This copies the data from kernel to the user process and does it with all the safety checks that one would expect a kernel to do. Hopefully there's no error. If the residual is now 0, then the read is complete, and we can just go ahead and wrap up, just doing some bookkeeping. If in case we've exhausted an entry or exhausted the list of entries altogether. And once that's done, we can then regrab the spin lock again and put whatever data is left back into the hash table. Now, of course, the problem is that while we were doing that, another thread might have added something to that table. And so now you have to merge them together. And so that's what this code does. And it does that by simply chaining the two lists together in the correct order. And then find queue, this searches the hash table using the, and this is how kernel code basically walks a hash table looking for something. With a sanity check that the thread control, the thread block, should match what we expect it to be. And then destroy queue and remove head entry. So not a whole lot of code here. It's a proof of concept, really. For example, there's a lot of functionality that could be added. Right now it's expected that the only thread really that's expected to read a queue for a thread is the thread that created it. This need not be the case, of course. Thread descriptors can be passed to other threads or even other processes by various means. It might be nice to have a file handle that reads all messages logged for any thread of a process, for example, or any process of a process group. That could be a useful extension. This does not have the best performance that's possible. I have a hash table, and that hash table has a global mutex on it. So obviously that could be a point of contention. And strictly speaking, the hash table is not really needed because it's hashing on the thread ID. Well, every thread already has a thread control block, so why not just simply put the pointer, to this list of queue entries into the thread control block directly? And there's no reason, I suppose, why it can't be done. I just didn't want to mess around with it with a very critical system data structure. But it could be put there, in which case you no longer have a hash table and you no longer have the contention of that mutex. And that would be a whole lot better. So, and of course, there's a lot of functionality that's missing. If you had a test driver that was watching a lot of queues for a lot of threads at the same time, you would want to use a KQ or select. And I haven't implemented that yet. And unfortunately, when I look at the code for pipe, which does all that stuff, it was a little bit more complicated than I thought it would be. Part of the problem is that that code is extremely optimized. Unfortunately, it also makes it a bit difficult to understand as well. But in a perfect world, I would add the functionality in the device driver for selecting KQ, and also to switch blocking I/O on and off, if this was a complete implementation. You can argue that compiling this should not be triggered by invariants. Even in a debug build, you may not want this turned on because it'll probably slow things down more than a debug build already slows things down. So maybe you should have a separate macro to control this. So that would be a possibility also. But it is something I think ought to be in the kernel because I don't see any functionality like it, and it's probably one reason why there aren't that many unit tests or regression tests for the kernel. Because ultimately, it's very difficult to test for something where failure shows up as a kernel panic. There's really no deterministic way of triggering that panic. It generally requires that several things have to happen at the precise time. And it's very difficult for a test to recreate that situation. And I guess that's pretty much it. So any questions? Yes?
Yeah, so you said there's nothing like the no facility acquisition. Have you thought about basically piggybacking on dtrace for trace points? Because I see this as kind of similar functionality.
I'm not familiar with dtrace actually, so that might very well be true. Yeah, I don't know the answer to that. I guess I should, but I don't.
Dtrace is also one of the things I'd like to learn more about. From what I understand.
Yeah, I've never looked into it, so maybe it is. But nonetheless, there are still very few unit tests and regression tests because I did look there.
Oh yeah, sure.
And they weren't generally using, they did not seem to rely on dtrace or any other special kernel debugging facility Yeah, they just basically exercise the API the way a user process can access the API, and they just simply verify that it did what it was supposed to do. And that's all fine and wonderful, but that doesn't prove that there isn't there isn't a race condition in there. No other questions?
I have a very basic question. So
Okay.
How does Kernel get away with the authors?
Very, very, very carefully. There are lockless data structures. You often use them in conjunction with atomic CPU instructions. In the case of Intel, that'd be a compare swap. Although many instructions in x86 can be made atomic by prefixing the appropriate lock prefix code. And you have to be very careful. It is very hard to do and very hard to get right. So you want to do it only when it really matters to performance. And looking up a file descriptor certainly would qualify for that because it's a very common operation. And just
What is the basic construct that prevents two things from running
basically, like I said, it's using an atomic instruction. I mean, that's what you have to use. In the old days, when you only had one CPU and only one core and no hyperthreading, it was sufficient to disable interrupts. And that was sufficient. That, of course, those days are long gone. And so you have to use atomic instructions. And basically, as in the case of Intel, you use a compare swap. And how that works is that you provide a memory address, you provide the data that you want to store into that memory address, and you provide the data that you expect to already be in that memory address. And so, as a single atomic operation, that's atomic with respect to all other CPUs in the system, and that includes physical CPUs, not just other cores on the same CPU, it reads the memory location, compares it with the expected value. If they do not match, the instruction ends right there and sets a condition flag. If they do match, it then stores the new value. And this is an uninterruptible atomic operation with respect to all other CPUs. It also does a memory barrier, forcing all loads and stores before that instruction to execute relative to any loads and stores that come after that instruction from the viewpoint of other CPUs. Because again, a fact of life with modern CPUs is that the order in which data is stored, loaded or stored in the instruction stream only has a vague resemblance to the actual order data is fetched and stored to physical memory. So you have to worry about that as well. So in the case of the file descriptor table, what it's doing is it only does a lockless lookup, I think. And so when a thread needs to look up the file descriptor entry for a number, for a descriptor ordinal, let's say you read file descriptor 0, it has to find the file descriptor table and subscript it. Well, there's a pointer in the thread control block that points to the file descriptor table. So you load that pointer, and then you load something at at subscript 0. Well, while you're doing that, of course, theoretically, another thread could be opening a file and it exceed the capacity of the table, and therefore has to allocate a new one and replace the old one. That's why you can't delete it, because that will cause a dangling pointer. However, even though it hasn't been deleted, it still could be out of date because it's loading information for the file descriptor from a block of memory that's logically deleted. You're supposed to, so it has to detect that it has gone and that it has been reallocated and then go and refetch it from the new one. And actually, it'd probably be easier just to find that code and show it. So it's in here. And let's see, what is that function called? Fget? Underscore fget.
It's actually pretty nasty.
Yeah, it is.
Because it's not a simple atomic, because we have a whole structure that has a pointer and all this stuff, which takes forget.
Right. So there it is. And, oh yeah, fget unlocked. That's it. Yeah, okay. Fget unlocked. Right. So first it checks it's not out of range. Fetch descriptor locklessly. We avoid f-drop races by never raising a ref count above 0. So it, right, it's not using an atomic add. So it's using a, get past all the capabilities check here. Yeah, it's nasty here. Yeah, so right. So if the count is 0, that's what right. There's a count on the file descriptor table. If it's 0, that means it's inactive. No thread is currently pointing to it, and so that's where you have to force a reload. And here it basically outsmarts the optimizer by marking it volatile. Therefore, actually forcing it to reload it, so the compiler can't say, but we've already fetched this field, so there's no need to fetch it again. You know, we'll just use the value we already fetched earlier. And marking it volatile stops the compiler from doing that. And then here's where we do the atomic construction. So doing a compare set, acquire with an acquire barrier, blah, blah, blah. And again, this is obviously very hardware platform dependent how that is implemented. On Intel, you can use a compare swap or compare exchange or whatever the damn thing is called. You know, on other platforms, it might be a load linked, set linked. Then you have PA risk, which is totally branded with atomic constructions. But you know, just use this, and that's implemented in a platform-specific way. So that's where the atomic construction is done. That increments the count in an atomic fashion. You know, that's with respect to every other CPU in the system. And then once that's done, you know, you can finally go and dereference the pointer and return it. You know, you've now got the file descriptor. So that's so that's how you do lockless data structures, and it is very, very hard to get right. It's very easy to fall into traps where you can use an atomic construction, for example, to add something to push something onto a linked list or to remove it from a linked list, but you got the ABA problem in which even using a compare swap instruction to verify that the old value is what you expect it to be, that's not safe enough actually. The odds are very, very low they'll bite you, but it still could bite you. And it's a common mistake when doing lockless data structures. It's very, very hard to do right. And so you need to do it only where there's a real benefit and make damn sure you don't screw up. But operating systems are a place where you do it.
Thanks.
Also, part of what we do is kind of gross. So you have the an array of things that have pointers to the low process figures. Anytime we have to make that bigger because we load in more files, we never free it. So I need to, part of the magic in that nasty function is we actually may look at the wrong array. And we kind of notice that doesn't see a file because the count is 0. It's actually, it's for the file, the count is 0. We'll notice and actually refetch the array pointer, top level. But to make that work safely, we have to allow feds to be able to read the old ones. So we can't freeze them until the process ends. It's kind of broke. So we'll actually keep multiple copies of the array around until the process actually goes away.
Which is the point that's junior job, was to free it up in a single thread, single process context where you know no one else could be referring to it. I guess we're done.